Hey folks, and welcome to 7.2. I'm going to try and make these videos while I have my cold that's hopefully fading quickly, but I might pause and restart, and I apologize for the quality of my voice right now. In section 7.2, we focus a lot on graphs because the graphs themselves and the functions that they're based off of are what make this unit unique. We'll revisit old concepts, but we'll just apply them to new shapes. So this first video is about motion graphs, and it all starts from the way that we graph position functions for objects in simple harmonic motion, and the types of function we use to model them. So I'll show you in class where these equations kind of come from. If you're taking pre-calc or you've taken pre-calc, then you've seen a lot of where these equations come from already, but there's like a clue left in this equation. So there's two possible equations that you can use, and they're kind of, in this course, they're interchangeable. In a pre-calculus course, you would learn like how to transform between them and shift them, but in this course, we're really just going to show you these two functions and how you can use either one of them depending on the situation. So they are the same format. One is cosine, one is sine. We have a cosine times the cosine of 2 pi ft, and then for the other option is a sine 2 pi ft. It's important to note that time is the variable in this equation, and so this function represents what will become the graph of position versus time. Either function is fine. I'm not going to write that, but you can use either function to model position versus time for an object in simple harmonic motion, but it's important to note this function, the cosine function, it begins at the maximum displacement, which has a name that you can clearly see on the video already. Whereas the sine function, in other words, the cosine of 0 is 1. And so if I were to put in 0 for the time into this cosine function, I would get x equals a. And that represents the maximum displacement. On the other hand, if I put 0 into this sine function, the sine of 0 is 0. So the initial position, according to this function, is 0. So this function begins at equilibrium. And the way that you would approach them in this course is kind of the other way around. If you saw a graph of simple harmonic motion, you could immediately determine whether it was a cosine or a sine graph based on whether it started at the maximum displacement or at equilibrium. Maximum displacement would be x equals a. And I've defined a down here as the amplitude. I've talked about it in other videos, but it's the maximum displacement from equilibrium. And then the sine function begins at equilibrium, which is x equals 0. So for this video, I'm going to use the sine function to model the graph for no really good reason other than you can see one cycle in all the parts right in a row, but either one is fine. All right, the real centerpiece to this video is this set of motion graphs that I've unfortunately put way over the left side, and I wanted to put some stuff in the margin. I'm going to draw a position graph. Before I do that, I actually want to show you the power of Desmos. So I have in Desmos these two functions, the cosine and the sine. Desmos is awesome because you can turn the functions on and off. So there's the cosine function. You can see it begins at 1 because this slider sets the amplitude at 1. Cosine function starts at 0 because that's the cosine of 0 value, and it gets up to a maximum amplitude of 1. Now amplitude goes in both directions, so it can be a position of positive 1 or a position of negative 1, and either one is still the same magnitude. This function, the way it's set up, a is in front of the trig function, so the value of a determines the height of the trig function, and so this is like a nice little animation that shows you that happening. The frequency value tells you how squishy this function is going to be. So the frequency is inside the trig function, so it's going to modify that coefficient in front of the variable. And so as the frequency goes down, the function spreads out, and as the frequency increases, the function squishes. So the graphs can be used to view like which whether you have a high amplitude or low amplitude or a high or low frequency. All right, so let's draw this graph. Now the position graph I'm going to draw, I put 4 hash marks here on all the graphs you're going to see for this entire section, and they're going to represent the 4 segments of this object's motion. And so if we start at 0, 2 hash marks represents half the amount of time for one period, and the 4th hash mark represents a complete period. So I'm just going to graph 1 cycle on this graph. If you wanted to graph more, you would just keep going. This hash mark here on the y-axis is positive A. It's the maximum positive position attained by this object, and this lower hash mark is negative A. So the amplitude goes in both directions. So I can draw as best I can a trig function or a sine function that goes like that. So there are 4 segments to simple harmonic motion. From equilibrium out to the positive most position, from that position back to equilibrium, from equilibrium to the negative most position, and from that position back to equilibrium. Now, if you remember like the cosine function we just looked at, that one starts at a different position. So we have from the amplitude, positive amplitude to equilibrium, down to the negative, back to equilibrium, up to positive. So the sequence is the same, but the beginning part of the cycle can change. All right, so this is our graph. Now, what we want to remember from the position graph is the slope of this graph equals the velocity. And so trig functions have a constantly changing slope. We're going to play this game of like maximum, minimum, 0. And if you look at the way this graph starts, it starts with a very positive slope. So the velocity function is going to start at the maximum value. Now, because it's velocity, it's no longer amplitude. It is the maximum positive velocity that object's going to have. If I fast forward to the first hash mark, this line it comes up, reaches its peak, and starts to come back down. At that highest point, the slope is 0, and so the velocity is going to be 0. If I go to period over 2, that's the most negative slope that I see in this entire graph, and so I'm going to be way down here. This is negative of the maximum speed that the object has. So the 2 extremes are now maximum and minimum velocities. And if I keep going, I've plotted these 5 points here that I'm now going to connect. Because this first graph shows a constantly changing slope, I have to show a constantly changing slope for velocity. And so I'm going to not connect these with a straight line, but I'm just going to draw a new trig function. Now, this particular trig function is a cosine function, and when you learn calculus, you will learn that the derivative of a sine function is a cosine function. But that's not important. What's important is that you can like translate between them, but also that you can just read this. So in this velocity graph, we have some like maximums and we have some velocities of 0. So this maximum velocity, that happens at the very beginning, the very middle, and the very end. Well, those 3 moments on the position graph are when the object is passing through equilibrium. So that maximum velocity happens when the object is passing through the equilibrium. So the forces line up so that the acceleration has happened and the maximum amount of acceleration in the same direction ends when it gets to equilibrium. And so that's where our maximum velocities are going to be. The other thing I want to notice is when the velocity is equal to 0. So that happens here and here. Well, those 2 moments are the extreme moments in the position graph. So that happens at the amplitude. The maximum positive and the maximum negative displacement, that is where you get a velocity of 0. And so last we're going to do the acceleration graph. We're going to play the same game, and for a velocity, the slope of a velocity graph is equal to the acceleration. Sorry, the video recorder cut out, so I'm just going to pick up where we left off. The slope of this velocity graph is equal to the acceleration. At the beginning of this velocity graph, we're at the highest point. When we did that analysis of the slope of the position graph, we talked about how at the highest point, the slope is 0. So that's where I put this dot here for 0 acceleration. At the first hash mark, we have a velocity graph that has the most negative slope that it has in the entire graph. So we put the dot at the lowest point for acceleration. That is the maximum acceleration in the negative direction. We get the lowest point in the velocity graph. The slope once again flattens out very briefly, so we get an acceleration of 0. When we get to the third hash mark, we have the most positive slope that we see on the graph. So we put a dot at the highest point. That is the most positive acceleration that we have for this graph. And then we get to the last hash mark, which is at the period of, or 1 period of oscillation. We are back at the peak. That's another acceleration of 0. So this graph is going to look like this. And again, if you go take calculus or you're familiar with calculus, this graph is the negative sine function. And so if you take the derivative of a cosine function, you get the negative sine function. But that is not important. What is important is we can identify when the maximum acceleration happens. Well, that maximum acceleration was here and here. And those positions are actually at the amplitude. So the maximum acceleration is whenever this object gets to its amplitude. Maximum acceleration at amplitude. I'm using amplitude as a shorthand here, right? We mean that when it gets to its maximum displacement, that's when it has its maximum acceleration. And then acceleration equals 0 at equilibrium. So when the object is passing through equilibrium, it's going as fast as it's possibly going to go, or as it's ever going to go, but it also has a 0 acceleration. The last thing I want to point out in this video is, if I zoom out just a little bit, we can see the position graph and the acceleration graph together. When the position is at its most positive, the acceleration is at its most negative. When the position is at its most negative, the acceleration is at its most positive. So acceleration is always opposite the direction of displacement. And that is part of a linear restoring force, that the force is always pushing or pulling the object back toward equilibrium, and so that acceleration is always going to be in reverse for whichever way the displacement is.